Amir Karamlou from Massachusetts, from MIT. Amir is a doctoral candidate in the Engineering Quantum Systems Lab at MIT and a recipient of the NSF Graduate Research Fellowship. His research focuses on experimental quantum computation using superconducting qubits, and in particular, quantum simulation. Prior to pursuing a PhD, Amir graduated from MIT with a Bachelor of Science in Physics and Electrical Engineering and Computer Science and a Master Engineering in Electrical Engineering and Computer Science in 2018, where he worked on quantual and high-fidelity readout of NV Center in Diamond. Outside of the lab, he's involved with Qubit by Qubit initiative, which some of you guys might already know, as the lead instructor of the year-long introductory quantum computing program aimed towards high school students. And with that, I'll pass it on to Amir. And
thank you so much.
Applause. Thank you.
Yeah, thanks everyone. Yeah, and it's great to be here. And I think we've seen the first slide for long enough, so maybe I'll just skip through it. So the idea of quantum simulation was initially proposed by Richard Feynman in 1981, so 41 years ago, as the original application for a quantum computer. So Feynman thought, hey, simulating quantum systems on a classical computer is expensive. Why don't we use another well-controlled quantum system to simulate the desired quantum mechanical system that we're interested in studying? So to this end, classical computing resources required for simulating quantum systems grow exponentially. So with every two-level system that I add to my larger system, I need twice the amount of memory. And I think yesterday Nathan did a good job of emphasizing actually how costly it is to store the state of a quantum system properly in the classical fashion. Now, specifically, we're interested in interacting many-body quantum systems, which exhibit very interesting physics, but they're hard to study analytically because they're very complex systems, and we can't simulate them on a normal computer. So this is why we propose, and something that we've been working on, is to actually simulate these many-body quantum systems on a quantum device in order to learn physics that we have no understanding of right now. And of course, to give you guys some flavor for why we're interested to study this physics, you can think about like solving problems like better materials engineering, better or understanding things at the nanoscale better. Okay, so my outline of the talk will be as follows. First, I'll talk a little bit about what superconducting quantum circuits are and how do we build superconducting qubits. Then I'll talk a little bit about some of the quantum simulation results that we've had in our lab. And if time permits, which it probably will not, I'll tell you guys a little bit about the way forward and our current experiments. So with that, let's get started on talking about superconducting quantum circuits. So a lot of you hopefully are familiar with what an LC circuit is. It's just a circuit with an inductor and a capacitor in parallel. And the idea here is that basically if I put some energy in my system, the energy will flip-flop between being stored in my inductor to being stored in my capacitor. So if I were to write a Hamiltonian or like an energy equation for this LC circuit, it'll look something like this. Again, you see the first term basically is the energy of the capacitor with some amount of charge, which we can extract with this operator Q. And the second term is the energy stored in the inductor. So that's just the energy in the system. Now, the physicist in me can rewrite this equation in form of this n hat operator, which is a dimensionless charge number operator, and this little phi operator, which is a reduced flux quantum operator. And again, here phi is the flux that's stored in the inductor. So again, this EC, and again, this is the part that I really want you guys to pay attention to if you're not that familiar with Hamiltonian and quantum mechanics. So the EC here tells me that, again, it's the energy that's stored in the capacitor, and it goes as 1 over CR, the capacitance, and the EL is the energy stored in the inductor. And again, it goes as follows, but again, 1 over L divided by R. Now, for those of you who have looked at an LC oscillator either in your differential equations course or quantum mechanics course, the LC circuit behaves like a harmonic oscillator. And again, in the quantum limit where we're operating this device, it will be a quantum harmonic oscillator. Now, the oscillation frequency of this oscillator, omega r, is 1 divided by L over LC, which is, again, something that we're familiar with from just the classical world. And I can write it as I can write an equation as a quantum harmonic oscillator where these A daggers and A's are the creation and annihilation operator. So if I were to draw the energy diagram for this system, it looks something like this. There's going to be a quadratic potential, which should make sense, again, based on the fact that I have terms like phi squared here. And then there are energy levels that are all equally spaced. Now, if actually, maybe I can ask this question from you guys. Can I use this system as a qubit? I have a 0 state and a 1 state. Can I use use those two as a qubit? Yeah, I'm seeing some head shakes. The reason why is, OK, I can try to apply a pulse that drives a transition. Like basically, it's at this energy h bar omega r that drives the transition between the 0 state and the 1 state. But the problem with that is that it will also drive a transition between my 1 state and a 2 state, my 2 state and the 3 state, and all the states. So effectively, I have no way to properly isolate out the first 2 energy levels that then I can use as a quantum bit of information. OK, so the LC oscillator is not exactly the qubit that we're looking for. But now let's talk a little bit about another tool that we have available to us when we talk about superconductors, and that's a Josephson junction. So a Josephson junction is when I have a superconductor let's say 2 superconductor leads with an insulator sandwich in between. Now, normally, if I didn't have superconductors here, if I had a normal conductor, I wouldn't get any current flowing through this junction, right? Because there's an insulator in between. However, since I have a superconductor and the insulator is very thin, what happens is that the current, or let's say charged particles, can tunnel through this barrier. Now, in doing so, they gain a phase, but still they can tunnel through, so I can get current flowing through the circuit. So what I told you guys is that in doing so, they gain a phase, that I'm showing with this phi, and the current and the voltage across this junction, this Josephson junction, follow these relations. Now, if I fast forward a little bit, basically by doing a little bit of math, I can get what the effective inductance for this junction is. And what you see is that now this inductance for the junction Lj is no longer linear, but rather has some cosine dependence on the phase difference between, from one end of the junction to another. So with that, I can build a qubit out of this, actually, and I'll tell you guys why. So on one end, I have my capacitor from the LC circuit that we discussed. And on the other end, I replace my inductor with this Josephson junction that, again, is a nonlinear inductor. Now, let's see what happens when I do that. So basically, the equation that I had for the LC oscillator, the Hamiltonian, will look something like this, where now the energy of the Josephson junction has some dependence on the critical current of the junction. And this is something that we can actually engineer in fab. OK, so I'm just going to expand the cosine term. I get something that looks like this. This is the expansion. Now, if you look at the first 2 terms, right, these are identical to what we had for the LC oscillator. But we now get these additional phi to the 4 terms. And now, because of this additional nonlinearity that we have in our system, all of a sudden, the energy difference between 0 and 1 is different than the energy difference between 1 and 2. So with that, I can actually use 0 and 1 as my qubit subspace. And I don't have, we do have to worry about the higher energy levels, but at least there's a unique transition between 0 and 1. Now, in the case of the transmon qubit, which is what I told you guys about, which again has a capacitor and a Josephson junction, this energy difference, so the energy difference between 0 and 1 and 2 is small. It's like of order of, let's say, if the energy, the frequency to go between 0 and 1 is 4 gigahertz. The difference in frequencies is 200 megahertz. It's small, so we do see contributions from the higher levels, but nevertheless, the transmon, what I just told you guys, is actually a qubit. And now if I apply a pulse that is at this energy difference, that has energy that's equal to the energy difference between 0 and 1, I get a transition between 0 and 1 only, and not any of the other states. So this is how we build a superconducting qubit. Now, what if I want to be able to change the frequency of my superconducting qubit? So, what I told you guys earlier is that I can set the frequency of my qubit by, choosing the right capacitor and the right Josephson junction. But I can also play a smart trick in order to be able to change my qubit frequency in situ. And I can do that by using a superconducting quantum interference device, or a SQUID, which looks something like this. So now instead of using a single Josephson junction, I build a circuit with 2 Josephson junctions in parallel. So this is Josephson junction number 1, junction number 2. And when we have a circuit like this, this part has to follow this relation, where phi 1 and phi 2 are just the phase across the junction, the first junction and the second junction. And this phi e now is given by the external magnetic flux that's going through the SQUID loop. And this is something that we have control over as experimentalists. So, the Hamiltonian of my system will look something like this. Let's not emphasize it. But when I look at the transition frequency from 0 and 1, it has a cosine-like dependence on the magnetic flux that goes through the SQUID loop. So essentially, by changing the flux bias as phi external, which, again, we can do in our experiments, we can change the qubit frequency. And in fact, with superconducting qubits, we can engineer qubits with different frequencies, again, different responses to flux bias, different anharmonicities, and different sensitivity to noise sources. So this is the workhorse of what we use for our experiments in our lab, or I should say most of our experiments, because there's a lot of additional research into novel types of superconducting qubits. So I showed you guys circuit diagrams, but now let's see what these superconducting qubits actually look like in real life. So what you see here is a superconducting transmon qubit. So this big pad that's in the shape of a plus is the capacitor, and then there's a ground plane everywhere. So this is the capacitor pad. Now what you see up here, that's the readout line. That's what we use to read out the state of the qubit. We have the charge line here, which is what we use to apply an X or a Y gate to the qubit. And then the flux line here, which is what we use to actually apply the flux bias needed to change the qubit frequency. And this small bit that you see here, which I'm going to zoom in next, is the SQUID loop and the Josephson junction that I told you guys about. So just to put things into perspective, you can see how large the capacitor of the transmon is, especially compared to how small the SQUID loop and the Josephson junctions are. So again, this is the SQUID loop that I told you about. There's a Josephson junction here and a Josephson junction there. It's connected to the capacitor, one pad of the capacitor on one end and then the ground on the other end. And now if I zoom in even more, we can see the Josephson junction and what it looks like. And again, the takeaway message is that the Josephson junction is a nonlinear inductor that we can use to make, to make qubits that have unique transitions between 0 and 1. Okay. So now that we've talked about a single qubit, a single transmon qubit in particular, let's talk about how do we actually couple multiple qubits together, make multiple qubits talk. And again, this is what we need to build a quantum processor. So the way that we do it is through capacitive coupling. So let's say we have one qubit here, one qubit there. We just put a capacitor in between, and that's how our qubits talk together. Now, for those of you who are interested in the physics of it, the interaction Hamiltonian will depend on the charge or the voltage here on one node of the capacitor and the voltage of the other node of the capacitor. And of course, I can write this in terms of the number of charge particle operator, and then what we see effectively is that we get the following Hamiltonian. Now, the takeaway message here is the first part is just the energy of independent qubits, each individual qubit. So I have two qubits here, qubits 1 and qubit 2. The second term is the interaction term. And what this gives us, again, what I want you to take away from this Hamiltonian that I have, for those of you who are not that comfortable with quantum mechanics, is that you get an exchange type of interaction with a Hamiltonian like this. So if I put a charge, like let's say a photon or an excitation on one qubit, it'll hop over to the next qubit and back. It'll flip-flop back and forth. That's the type of interaction we get when we go in the right frame with this Hamiltonian. Okay, so I told you guys about the theory of superconducting qubits, but how do we operate these devices now? So this is what my room temperature setup looks like back at MIT. We're using this to operate a 16-qubit sample right now. We have some arbitrary waveform generators that can generate pulses with the resolution of 1 nanosecond. Now, we can use these to control, to apply the flux bias needed to control our qubit frequency in order of nanoseconds, so very fast. And also, we can use these to control our microwave sources down here, which then we use for either reading out the state of the qubit or applying XY gates to our qubits. And of course, we have some atomic clocks to sync up all of our devices and some DC bias sources down here. And then we combine all the signals before sending them down to our fridge. Now, the next part of the experiment is a dilution refrigerator. And this is what Nathan was describing yesterday in his cartoons. I like to think it looks a little bit better in real life than what was depicted. So the dilution refrigerator essentially cools down our lines and our signals gradually. So we start at the 4K stage. Well, actually, it starts at room temperature, then goes to 50 Kelvin, then 4 Kelvin, then 1 Kelvin, 100 millikelvin, and then 10 millikelvin is the temperature at which we operate our superconducting qubits. And the reason why we need to get our devices so cold is, well, one, in order to turn our aluminum actually superconducting. So the transition, the TC, which is the temperature at which aluminum goes superconducting, is about 1.2 Kelvin. Again, much larger than this value. But the second reason why we go so cold, which is the more important reason, is that we want the thermal energy in the environment, which is just Kb, being Boltzmann constant, times T, to be much smaller than the transition frequency between our 0 and 1 state to avoid any accidental thermal excitations. And then also in this fridge, we have filtering and attenuation, which is necessary to reduce thermal noise or other noise sources that our qubit experiences from the room temperature electronics. Okay, so I told you guys that our sample sits right over here. So this is what the package that I'm using to house my superconducting chip looks like. So these are, again, all the microwave wires that are necessary to communicate with the qubits. And I guess this picture was what Nathan described as Medusa, a Medusa-like thing yesterday. And looking at it, I don't disagree necessarily. And finally, our quantum chip actually sits inside this package in the fridge. Now, what I'm showing here is a 16-qubit sample that I'm using for my experiments currently. But before we get to that, I'll talk a little bit about the experiments that we've done on a 9-qubit sample. And here, you can see each transmon that I showed you is false-colored in, I'm going to call this blue. I'm sure there's a proper name to it, but I say it as blue. And you can see that there's a piece of metal that connects these, these pairs of transmons. And that's the capacitor that I showed you guys that we use for coupling our qubits. Okay, so with that, why do we use superconducting qubits for quantum simulation? Well, there are a few platforms. First of all, there's a strong interaction between the qubits. Since we can design these capacitors to be to be large within a certain limit, we can make these qubits talk together much better than other platforms can. And basically, this means that we can get a lot done within the lifetime of our qubits. So what I have here, again, for those of you who are not technical, is that my coupling rate compared to my energy relaxation rate is about 2,000 times larger. So again, ideally, I should be able to squeeze in about 2,000 operations before my qubit relaxes and is not useful anymore. And of course, another benefit, because of the stronger interaction, is that it's much faster for superconducting qubits to run the same quantum circuit than it is for trapped ions or atomic systems, because they don't have as strong of an interaction. And by faster, I mean wall clock time, like how much time in real life it takes. Now, the next one is that we have a high degree of control. We can set the frequency of each site with an average accuracy of 200 kilohertz. Which again, compared to this interaction strength that we have, which is a natural units of our system in a sense, it's 100 times better. So we can get down very accurate. We have access to individual and simultaneous site operations, think single or 2 qubit gates with high fidelity. So this is this number, the 99.9 plus fidelity for single qubit gates is from the experiment that I'm doing. We've gotten this up to 99.99% in our lab. And finally, we have individual and simultaneous tomographic site readout. So we can read out the value of each qubit at the same time, but not just along the z basis, but along the x basis and also the y basis. And again, people have used these tools for quantum computation. I mean, we've seen a lot of demonstrations from Google that you can tune up high fidelity single and 2 qubit gates and then execute a quantum circuit. But also, these properties are very useful if you just want to focus on quantum simulation. OK, so with that, let me tell you guys a little bit next about some of the quantum simulation results that we've been working on in my lab. So the superconducting quantum processor that we've used for our experiments that I'm going to talk about is this 3x3 9 qubit sample. So we have 9 flux-nimble transmon qubits. And then we have a local flux line for each site, which allows for individual site frequency control. And again, I told you guys that we can tune the qubit frequency of order of nanoseconds, which is very fast. And finally, it is in a 2D grid. So we have 2D connectivity with nearest neighbor coupling. And with all this being said, this system can be described by something that's called the Bose-Hubbard Hamiltonian, which looks like this. So the first term of the Hamiltonian is the energy of each site. Here, this epsilon I depends on the qubit frequency, and that is something that I told you guys we have control over. And n is this number operator here is the number of excitations on each qubit. So 1, 2, 3, like where on the energy level you are. Now, the second term is the on-site interaction term. So this is the additional energy, you can think of it as an energy penalty that we incur when we add more than a single particle or a single excitation on a given site. So, if n is equal to 0 or 1, this will be 0. But once n goes to 2, you get an additional u over 2 contribution to your energy. And the third term is a coupling interaction. So this is just the interaction. This is basically just comes as a result of the fact that these 2 qubits are coupled together. And again, when basically the interaction is, one qubit gains an excitation, the other one loses an excitation. So it's that exchange interaction that I told you guys about earlier. Now, for transmon qubits, the on-site interaction term U is governed by the qubit anharmonicity, which is about, the magnitude is about 200 to 300 megahertz. And it's much larger than our nearest neighbor interaction, which has a value of roughly 10 megahertz. So we're between 20 to 30 times smaller, or J is between 20 to 30 times smaller than this U. So effectively, it's very energetically disfavorable to populate the second excited state by just letting the system evolve and interact when you only have single particles, like single excitations in your system. So because of that, we are placed in this something that's called the hardcore Bose-Hubbard regime, which again just means that every site can only have at most 1 excitation. So 0 or 1 particles. OK. So with that, now let's talk a little bit about our experimental sequence. What is the sequence that I'm actually using in lab to show you the data that I will in a moment? So first, by applying a DC flux, again, using the DC sources that I showed you guys, we tune all of our qubits on resonance. Next, I detune my qubits, again, of the time scale of nanoseconds using my fast flux capabilities with those arbitrary waveform generators that I showed you in a checkerboard pattern that looks like this for state preparation. Now, the reason why we do this checkerboard pattern is that we want the neighboring qubits to be far detuned from each other such that they don't interact when we're trying to prepare a state. So okay, here we essentially turn off our interactions by detuning our qubits. We apply single qubit gates to whichever site we desire. Then we bring the qubits either on resonance or near resonance to emulate some desired Hamiltonian H. And we allow it to interact, we allow the system to interact for some time t, some evolution time t. And then we detune the qubits again to freeze out the system dynamics, and then we read out the state of each qubit at this point. So this is the sequence that we use for all the experiments that I'm going to show you. The first set of experiments are quantum random walks. So I told you guys that I have control over the frequency of all the qubits in my system, so I can just detune 2 of them so far away from the other qubits such that they don't interact with the rest of the system. And by doing so, I can carve out a 1D chain from my 2D lattice. And I place an excitation on one end of the lattice. And what I observe is a quantum random walk. So here, if this were to be a classical process, I would expect a slow, diffusive propagation of my particle. But instead, what I see is a ballistic transport, like something that goes linear in time instead of square root of time. And that is a signature that something quantum's happening. So a classical random walker moves away from where it started as basically with a standard deviation that scales with square root of t, whereas a quantum random walker moves away with a standard deviation that scales like t. And here we can see that things are moving linear in time instead of as square root of time. Now, for those of you who are interested in connecting this back to quantum algorithms, the nature of the speedup that we see with a quantum random walk is similar to the speedup that you see with the Grover search algorithm. With Grover, you get a square root of n speedup, a quadratic speedup over classical search. With quantum random walk, you also get a quadratic speedup over a classical random walk. And again, Nathan talked about this a little bit. It has applications to quantum algorithms. So this was in 1D. Now I can repeat the same experiment in 2D by allowing all my qubits to actually interact this time. And here in 2D, because of the symmetries that are present in my lattice, the qubit will actually pass through, the excitation will pass through the qubits that are at the same lattice distance, you can think of it as Manhattan distance, from where I started at the same time. So this excitation will occupy qubits 4 and 8 at the same time, qubits 1, 5, and 9 at the same time, and so on and so forth. So because of that, I'm plotting the population, or rather the sum of the population or the probability of finding the excitation on the qubits that are at the same distance from the initialization source. And again, that's what I see here. I see that when I allow my system to interact for some time, detune, read out, I get the same pattern of particle probability propagation that I expected, from a 1D random walk. And of course, the particle propagation, which is, what you see here, it's like the probability of the particle being found somewhere. Exhibits ballistic transport and not diffusive. And that's the distinction between a quantum process, a quantum random walk, and a classical random walk. Okay, so I just told you guys that my particle will occupy the qubits that are the same distance from the initialization site at the same time. So I expect the entanglement in my system to propagate the same way. So I expect entanglement to be created and to move across my system as my particle propagates. Now, I can probe this entanglement by performing 2-qubit state tomography and actually extracting what the density matrix for any different pairs of qubits are. And I can use concurrence as a metric to quantify entanglement. Now, what concurrence tells me is how much 2 qubits are entangled. So if 2 qubits are not entangled at all, like they're in a product state, I'm going to get a concurrence of 0. And if they're maximally entangled, like think like a bell state, I get a concurrence of 1. And then I get some value in between if they're partially entangled. OK, so let's look at the concurrence plots that we get. So here I'm looking at the entanglement between. So basically, what I told you guys, what I claimed earlier, is that as the particle moves through these qubits, I get a surge of entanglement. So like, you can see that initially my entanglement's 0. They're not entangled. The particle passes through. And then I see that my entanglement value, my concurrence value goes up to something. It's like almost like 0.4. And then as the particle leaves, this value drops back down. And then, of course, like what I told you guys earlier is that my particle bounces back and forth. So it'll come back, leave, and so on and so forth. So we see the same thing for the other pairs. And basically, the takeaway message here is that if I look at how my entanglement is created and compare to what the particle population is, I see the same random walk behavior, the same behavior that I did with my quantum random walk. And the reason why is that in this limit, quantum information entanglement propagate the same way that my particle propagates. It just goes back and forth. OK, so with that, now let's talk a little bit more about quantum information propagation. So if I have some bit of quantum information in my system, and you can think of it as an operator or some perturbation, like some event happening, as time progresses, the information is dispersed throughout the system. And this is called information scrambling. So in order to actually find out what the information was, I need to do some complex operations, not just on a single site where my information was added initially, but on the full system. Now, if I had some way to rewind time, I would be able to retrieve back that initial bit of information. And this is called the Loschmidt echo. Now, let's say there's a secondary event, a butterfly event that happens. And this butterfly event, for those of you who are familiar with quantum mechanics, does not commute with my initial bit of information, which just means that it'll disturb it if they're too close. Now, if this event is outside the light cone of my quantum information propagation, as I rewind time, I can retrieve that piece of information with no issues whatsoever. However, if it's within the light cone of my quantum information propagation, my information revival will be disturbed, or the reversibility will be disturbed. And this is the idea behind a concept called out-of-time ordered correlators, or OTOCs. Basically, the idea is that you can apply a butterfly operator, have some initial bit of information in your system, apply butterfly operator, and see when it messes up with the reversibility, with your ability to revive that initial bit of information. And with that, you can figure out how your quantum information actually propagates in your system. OK, so one question still remains. In order for me to be able to measure anything like this, I have to be able to rewind time in lab. And again, from quantum mechanics, we know that time evolution is a unitary process, so there should be a way to rewind it. How do we do that? So this is the Hamiltonian in the two-level limit that I described to you guys, the hardcore Bose limit. There's no possibility of exciting any higher states, and these sigma plus and sigma minus operators are just the two-level creation and operation operators. And then the sigma z just gives me the energy of each side. OK, so my natural time evolution has the following form. It's e to the negative iht. So if I want to evolve for minus t, I need to somehow realize e to the iht, so with no minus sign there. Well, one way of doing that is just somehow evolving my system under negative h instead of h. So essentially, the problem of rewinding time turns into the problem of somehow reversing the sign of my Hamiltonian in lab. OK, so how do we invert the Hamiltonian in lab? Let's look at the first term. So the first term is the exchange term between the qubits. And it has these sigma plus and sigma minuses. Now, if I sandwich a sigma plus or sigma minus between sigma z operators, Pauli z operators, I get negative sigma plus or sigma minus. So if I apply a Pauli z operator to every other qubit in my system, I'll be able to successfully invert the sign of all these terms. So, this is how I invert the sign of the first part of my Hamiltonian. Now, what about the second part, the on-site energy? Well, I told you guys that I have control over the frequency of my qubit at a nanosecond time scale. So I can just map this epsilon I value to negative epsilon I in my experiments. And that's how I invert the second part of the Hamiltonian. So basically, using this protocol, we're able to effectively rewind our time evolution. Can you give me a 1 minute heads up also? Thank you. OK, so let's put it to test now. I want to rewind time in lab. So in order to do so, I prepare an entangled state between qubits 7 and 4 by using the following circuit. I let my system evolve for some time t, and then I reverse time evolution. And then I perform tomography on these two qubits, and I want to see what is the final state that I end up with. OK, so this is what the results look like. Again, I just want to draw your attention to the red plot. This is the fidelity of the recovered state compared to what I started with. And you can see that we start at 1, and it remains pretty high. Now, it slowly decays in time, and that's due to decoherence, which is something that we don't have control over. But we've shown that we can successfully rewind time. OK, with that, let's use that as a tool now to probe quantum information propagation. So what I'm showing here is just a quantum random walk. Now, if we look at our out-of-time ordered correlators, we see that in the absence of any other particles, if I'm just looking at how information propagates through the same site that my quantum random walker was moving back and forth, the information propagation is identical to my particle propagation. And again, this makes sense with what we've seen so far. Entanglement, information, all of those propagate with the particle. If I add more particles, you see that the pattern at later times changes, and that's because of particle interference. However, the light cone of the quantum information propagation does not change. So the speed of quantum information propagation in your system is constant. Now, how it looks like at later time does change with the number of particles. And with that, I'm just going to skip through all of these. And I was, very ambitious. And maybe jump to this. Oops. Yeah, forget about the current experiments. Just jump to the summary of what I talked about. So we've shown that we can emulate the dynamics of particle transport and localization in our system. We've also probed entanglement propagation. And then we've observed quantum reversibility using a Loschmidt echo. And finally, we've studied propagation of quantum information using out-of-time ordered correlators. And again, I didn't get through the whole presentation, but the stuff that I talked about and with more details are in these two papers. And here's my email if you guys are interested about anything further with the work that I just talked about. So with that, I want to thank the organizers for really putting this together. It's hard work being on that side of the fence, dealing with all the technical issues in addition to all the getting the scientific aspect of a conference together. So thank you guys, and thank you all for your attention.
Thank you very much, Amir. We're really sorry about all the technical difficulties here. We have some time for a few questions, if there are any.
Oh, I like this.
Thank you for the presentation. For the concurrence plot for the different qubits, after the particle or the information passed for the first time, there was like a difference between the gap when the peaks converging.
Actually, no, I can even show it up here. So this is that concurrence plot that I was telling you about. So the first peak you saw for that new qubits at distance 1 was here, right? The second peak was here. The third peak was there. So the second peak was here. The third peak was there. So the reason why these two peaks are so much closer is that the particle is bouncing off of this end and then going back here. So that's why you see those peaks closer than these two peaks, for example. Yeah. So it's just because the particle is bouncing back and forth. And there's one other question up there.
Okay.
Yeah. Actually, I want to make one comment about the stuff I talked about. I think the most fascinating part of this research to me when we were doing it was actually observing quantum reversibility. Because that's something that you learn about in your quantum mechanics 1, right? That time evolution is something reversible. You can't rewind time. But actually to see that in real life and in lab was very fascinating. I think that was the most satisfying part of like all this experiments. So quantum mechanics is correct.
So you mentioned the checkerboard state interaction. Just a question. With the geometric layout, can you change it around, and is there optimized layouts, or it doesn't matter?
Yeah, so that's a great question. So the sample that I was telling you guys about, which is what we've done our work on, is this sample with fixed couplers. So again, the coupling between the qubits, the interaction is fixed, and it's set by, again, these capacitor pads. Now, one other way that we've extended our infrastructure in lab is by adding tunable couplers in between our qubits. So you can add another qubit in between your 2 operational qubits, which will act as a way to tune the coupling between the neighbors. So you can actually turn off the interaction completely by parking that coupler at the right frequency. And in fact, when you see like demonstrations from Google, that's what they're using nowadays. They're using tunable couplers to get operations with higher fidelity by turning the interaction on when they need it and very strongly on when they need it, and then completely off when they don't. Now, to answer the geometry question, so with superconducting qubits, once we fabricate this pattern, the pattern set, we can be smart and far detune or somehow turn off the interaction between certain qubits. But basically, that would be carving a pattern out of this grid. So we can't, for example, do a triangular grid if this is the chip that we have. Now, we could fabricate triangular chips, instead of having squares here, we can have triangles, and that is something we have a couple of chips like that in our lab. But that's something that needs to be done ahead of time. We can't do that in situ in our experiments.
What is like the maximum number of qubits that you can achieve in the system?
That's a very hard question to answer because it depends on what metric you define. I can go to MIT Lincoln Labs. I should probably end on that slide, acknowledging the teams. I can go to our sister lab who does our fab for us at the MIT Lincoln Laboratory and ask them to print out, make 1,000 transmons on a chip. And they can do it. The fabrication is not the hard part. The question is, how well can we control those 1,000? And that is why, companies, again, like IBM to a lesser degree now, they've kind of given up, at least for publicity reasons. But companies like in Google and IBM aren't just building 1,000 qubit processors off the bat, but they're starting with smaller processors. It's to ensure that you can actually control all your qubits to a good degree, and also your coherence time stay good. So, I mean, state of the art, IBM has a 127 qubit device. Granted that their gate fidelities are not as great because it's not using their latest research technology. And Google just published a paper with a 72 qubit device and tunable couplers that they use to demonstrate break even for quantum error correction. And that's a big deal. Because break-even is the point that when your quantum error correction code gets larger, your error rate actually gets better, which means that the error of each individual part of your error correction circuit, think of it as decoherence or gate errors, are good enough such that as you add more of them, your performance doesn't get worse. So yeah, that was on a 72 qubit processor. But again, the idea is that it is a scalable approach. And I think now that a lot of the issues around scaling have been at least addressed within the scales of let's say of 1,000 qubits, we're going to see those processors pop out in the next 1 or 2 years. I mean, IBM's already announced that they're going to reveal their 1,000 qubit processor, I think by 2023. So yeah, and I mean again, it's a scalable approach. Now, there are other reasons why, there are other technical challenges that need to be addressed, but we can talk about those offline, because I'm sure we're over time.
Yeah, perfect. We have time for one more question, if there's any. Yeah, I guess I'll just ask one question. What are some challenges you see on the road ahead for this type of stuff?
Yeah, that's a great question. Let me maybe go to another slide. Yeah, so wish I had a slide on what's the roadmap for scaling up these superconducting qubits. So one challenge, and this is a big one, is that in order to talk to your qubits, you need to go from this room temperature setup and somehow get the signal all the way down to your qubits. Now these require these microwave lines in your dilution refrigerator, which are bulky in a sense. So sure, IBM's building a larger dilution refrigerator, custom-made dilution refrigerator, in order to be able to house everything for 1,000 qubits. But at some point, this does become a limitation for how many qubits you can have in one fridge. Now, one active area of research is looking into whether we can actually generate all these microwave signals, all these signals that are required to communicate with our quantum processor inside the dilution refrigerator. That way we won't need all these lines, but we can reduce the overhead cost and just do the operation inside and maybe have a classical processor talk to whatever you're using for signal generation inside the fridge. So no, that's one bottleneck. Of course, it's always a question of doing materials research, building qubits with higher coherence properties, or looking into novel qubit architectures that don't suffer from the same noise sources that a transmon qubit does that I talked about. That's another one. Of course, another end is just a control question of how can we build, or how can we perform operations with 99.9% plus fidelity for 2-qubit gates. So I think those are the next, at least or some of the challenges that the field, especially for superconducting qubits, is facing right now. And again, there's active area of research going, but we still have time until we reach a point where these become a showstopper. There's still some more scaling to do, but we need to think about how to address these problems now.
Right, thank you very much.
Thank you so much.
Great talk.